All right, let's go through paper 6, which is the alternative to the practical for chemistry. This is for IGCSE from Cambridge International Examinations, May-June 2018, and this is variant 2, so the code is 0620/62. Let's get started.
Let it begin! Let it begin! Let it begin! Wait.
Question 1. The rate of reaction between an excess of dilute nitric acid and powdered calcium carbonate was investigated. The carbon dioxide it produced was collected, and the apparatus used is shown. Okay, so we have nitric acid plus powdered calcium carbonate. Acid plus a carbonate produces carbon dioxide. All right, so we have our powdered calcium carbonate in the bottom with dilute nitric acid. It's going to be producing little bubbles of carbon dioxide. The bubbles will go up the tube here, and as the reaction proceeds, that little plunger is going to be pushed out. And you can tell the rate of the reaction by how much the plunger is being pushed out. So the volume of carbon dioxide. A, complete the box to name the apparatus. This is known as a gas syringe. A gas syringe. All right. You can just call it syringe because it's just pointing to the syringe part. And the only thing that makes it a gas syringe is that it has this tube attached to the end going into the flask. A sketch graph of the results obtained is shown. So at time 0, the rate of the reaction is there's nothing, but obviously it increases very quickly and then it decreases. That's just a sketch. So label the y-axis. So the x-axis is time. What's being measured is the volume of carbon dioxide. So it's the volume of carbon dioxide. You're not given any units. You're not just supposed to guess. There's no units per time either, so there's no units to put in. It's just volume of carbon dioxide. 2. Explain why the sketch graph is horizontal at point X. Why does it go flat at the end here? Well, that's because the reaction has completed. There's no more carbon dioxide being produced, so it's flat. The reaction has completed. All right. What does that mean? This is explain. It's a 2-mark question. That is certainly not 2 marks worth. Well, the reaction is completed because there's no more calcium carbonate to be used. The reaction has completed, so no more calcium carbonate is being used up. Okay, you can't just say the reaction has completed because there's no more carbon dioxide being produced, because no more carbon dioxide being produced means the reaction has completed. So by saying about the reactants have used up, that's explaining why the reaction is finished. C. Draw on the axes the graph expected if the experiment were repeated using an equal mass of lumps of calcium carbonate. All the other conditions were kept the same. So lumps of calcium carbonate compared to powdered calcium carbonate, the lumps have a smaller surface area to volume ratio. So if it has a smaller surface area, that means the reaction is going to go slower. All right, so reaction starts off and it goes slower. How high does it go though? Well, there's the same mass of calcium carbonate, so that means it will go to the same level. All right, so it levels off at the same point. So this is the graph for lumps of calcium carbonate. Always label your additions to the graphs for the exams. All right, so as long as this ends off at the same level and it's lower than the original line, it should be good. D. Describe a test for carbon dioxide, and the test for carbon dioxide is the lime water test. The lime water test. Obviously, the lime water test is not made with limes. If you want to call it the calcium hydroxide solution, you can call it. You can say you can write down calcium hydroxide solution because that's what lime water is. It's calcium hydroxide. All right, and what happens if it's a positive result? If there's carbon dioxide present, then the solution will turn cloudy. So if carbon dioxide is present, the solution turns cloudy. You can say it turns milky. You can say there's a white precipitate produced. Those are all just fine. Question 2. A student investigated the temperature changes when 2 different solids, solid C and solid D, were dissolved in water. So they did 2 different experiments because they had 2 different solids. Experiment 1, using a measuring cylinder, 40 centimeters cubed of distilled water was poured into a polystyrene cup. And the initial temperature of the distilled water was measured. So we had a polystyrene cup and we took 40 centimeters cubed of distilled water and that went into the cup. Okay, 40 centimeters cubed. We have a thermometer in it, so obviously they measured the beginning temperature. 3 grams of solid C was added to the polystyrene cup, and the mixture was stirred with the thermometer. So we have into the cup, we have solid C. To start off with, it was 3 grams. The temperature of the solution was measured after 1 minute. Okay, and the procedure was repeated using 4 grams of solid C and 6 grams of solid C. A. Use the thermometer diagrams to record the results in the table. Okay, so down below here, we have a bunch of thermometers. All right. And this is an important part. It says calculate and record the temperature change in each case, including whether the temperature increased, and they did a plus, or decreased. That means you have to put a plus or a minus in front of each of the values in the final column. Okay? If you can't just assume that they know it's positive if you don't write a plus. All right, so if we look at this graph, we go between 20 and 25 degrees Celsius, and there's 5 gradations, so obviously each gradation is 1 degree Celsius. So this is 21 degrees Celsius. If you wrote in the graph like this, or in the table like this, you would get it wrong because it's already in the heading. All right, so next one is also 21 degrees Celsius. And the final one is 6 grams was also 21 degrees Celsius. All right, so the final temperature in the 3 grams, we have 15, 16, 17, 18 degrees Celsius. We have 15, 16, 17 degrees Celsius, and we have 15 degrees Celsius. All right, all of these values are directly at the line. There's no half a degree. They can do half degrees for these. And now is the part there, your complicated calculation. Final temperature minus initial temperature, 18 minus 21, that is minus 3 degrees Celsius. And 17 minus 21, that is minus 4 degrees Celsius. And 15 minus 21, that is minus 6 degrees Celsius. There we go. That's an easy 2 marks. If you can just follow a simple direction of putting the minus in front and read the thermometer. Experiment 2. Experiment 1 was repeated using 3 grams, 4 grams, 6 grams, and 8 grams of solid D. B. Use the thermometer diagrams to record the results in the table. Calculate and record the temperature change in each case, including whether the temperature increased plus or decreased minus. Okay, so basically it's exactly the same. We now have 4 different readings rather than 3, and we're using a different solid. So again, it should be another easy 2 marks. Okay, so looking at this one, this one went up to 22 degrees as the initial temperature. This one's 22 degrees, this one's 21 degrees, and this one's 22 degrees. All right, then we have the final temperature of 3 grams of solid D. That's 26 degrees. This is 27 degrees. This is 29 degrees. And this one is 33 degrees. 26 minus 22, that's plus 4. Remember, it says to put in a plus there. Don't just assume they know it's positive. They'll take the mark off because I've told you to put it in. 27 minus 22, that's plus 5. 29 minus 21, that's plus 8. And 33 minus 22, that's plus 11. There we go. That's that part of the question. C. Plot the results for experiments 1 and 2 on the grid. The 0, 0 point has been plotted for you. Draw 2 straight lines of best fit and clearly label your graph. Okay, so this graph, is quite straightforward. They have already labeled the axes. You don't have to worry about that. The only thing you have to worry about the axes labels is how much does each little square worth. Okay, so here we go up 5 degrees Celsius for 10 squares. So it's 5 degrees Celsius for 10 squares equals 0.5 degrees Celsius per square. That's just so that you know how high to go up, how much each square is worth. You do not have to show that on your graph. Now you're drawing 2 straight lines. Now quite often when you draw 2 lines on one graph, you should use different points. You should do one with a dot with a circle around it and one with a small X. That's what they like to see quite often. This one The 0, 0 point has been drawn as an X, and it's the same for both graphs. So you can choose. It doesn't matter. You won't lose a mark either way, according to the mark scheme and the examiner's report. So you won't lose any marks if you do both lines as X's, both lines with dot with circle, or one line with an X and one line with a dot with circle, as long as you have clearly labeled your graph. All right. Okay, here are the points for solid C. We have minus 3 degrees Celsius for 3 grams. We have minus 4 degrees Celsius for 4 grams. And we have minus 6 degrees Celsius for 6 grams. It looks like a nice straight line there. Okay, it is a nice straight line. It did actually say in the instructions as well to draw 2 straight lines of best fit. Okay, so if it says to draw a straight line, you don't have to guess whether you draw a curve or a straight line. It's with a ruler. All right, now we have to label that. And this one is solid C. Okay, this line is for solid C. Now let's do solid D. Okay, so here's the points for solid D. At 3 grams, it was plus 4 degrees Celsius. At 4 grams, it was plus 5 degrees Celsius. At 6 grams, it was plus 8 degrees Celsius. And at 8 grams, it was plus 11 degrees Celsius. And we can draw a nice straight line as well for that one. Okay, for that one, it's this point here at 4, it doesn't quite hit it. Almost misses the point. It sort of misses the point at 8 grams, but it is a nice straight line. All right, your line of best fit doesn't have to include every single point. It has to include most of them and the average of most of them. All right, so this is solid D. And it did say a straight line of best fit, so they don't want you to do point to point. And don't forget, you're supposed to be drawing these graphs with a pencil, because if you make a mistake, you need to be able to erase it without having the mistake showing through. So if it's a straight line, these ones are going directly through it. Just double check to make sure your points are in the right place, but if they are, then that's fine. D. Use your graph to estimate the temperature change after 1 minute if 8 grams of solid C were added to 40 centimeters cubed of distilled water. Show clearly on the grid how you worked out your answers. So you don't need to work anything out underneath here, you just work it out on the grid. So you might have noticed that I stopped my line at 6 grams. That is very important. Whenever you're doing a graph, you never extend your line beyond the points that you're given. It could do something completely different after that point, or on both sides. This one you're given a 0, 0, so you include 0, 0. But the other points you just don't include. On this graph, you do actually extend it beyond, because what you need to do is you need to find out what happens when you add 8 grams. All you do is extend the line all the way to 8 grams. Okay, the line is extended to 8 grams, and just draw a point there. That point right there is at minus 8 degrees Celsius. So the answer is minus 8, and the units have been written in for you, so that's okay. E. What type of energy change occurs when solid D dissolves in water? So when you dissolve solid D in water, the thermometer reading goes up, which means that the energy is being lost to the surroundings, which includes the thermometer, so that this is called an exothermic reaction. So it's an exothermic reaction. Okay. F. Suggest the temperature of the solution containing 8 grams of solid D if the solution were left for 2 hours, and explain your answer. Well, keep in mind the original time for this experiment was being measured after 1 minute. After 1 minute, you get a small temperature change. Maximum you've had in this experiment was 11 degrees. After 2 hours, all of that heat will have escaped into the surroundings and it will be back to room temperature. So the solution would be room temperature. It does say suggest a temperature, so you could say the solution would be 21 degrees Celsius or 22 degrees Celsius, because that was a starting temperature of the solutions to start with, which is highly likely to be room temperature. But this is a 2-mark question, and it says explain your answer, so that means it wants a because statement. Because the heat is being lost to the surroundings. So the solution would be room temperature because heat would be lost to surroundings. Certainly after 2 hours, it'll be back to room temperature. G. How would the temperature changes measured after 1 minute differ if the experiment's repeated using 80 centimeters cubed instead of 40 centimeters cubed of distilled water in each case? Okay, 2 marks. It wants basically something for each situation. However, it would be exactly the same for both. If you're using the same amount of calcium carbonate, but you're doubling the amount of distilled water being heated up, well, then it's going to only raise the temperature by about half as much for both of them. So the temperature change would be half as much in both cases. By saying in both cases, you're saying both solid C and solid D, and it will be half as much. That's 2 marks worth. H. Suggest one change you could make to the experiments to obtain more accurate results. Accurate means that basically the answer is more precise. It's not a rough amount. It's more close to the actual result. Explain how this change would make the results more accurate. Okay, so there's 2 things that are really the most obvious that you can use. One of them is you are using a polystyrene cup with the solution in, your solid that's being dissolved, and a thermometer sticking in. And when the solid dissolves, you're measuring the heat, the change in temperature, but a lot of the heat will be going out the top. So, an easy thing to do, put on a lid, and then you'll be able to measure the temperature change more accurately because it won't be cooling down as much as it is when the lid's not on. So you can use a lid. And why? So it reduces heat loss to the surroundings to make the results more accurate. You don't really need to say it to make the results more accurate because that's what the question's asking for. But you can if you like. The other thing that you can use, whenever it says you're measuring out a volume using a graduated cylinder. This is your graduated cylinder, beautiful. You can improve that by measuring the volume, improve the accuracy by measuring the volume using a pipette or a burette. Okay, burette or a pipette, because the diameter, the section that is measuring it, is a lot wider in a graduated cylinder than in a pipette or a burette. Okay, so that is a way to improve the accuracy for any experiment measuring the solution with a measuring cylinder, is to use a pipette or a burette. And I suggest how the reliability of the results could be checked. Now this is an easy answer because it's the same for any experiment really. Reliability means you can trust the results. How can you trust it? Well, because you've checked again and again and again, you've repeated it, and you've taken the average. So reliability, the answer for reliability is always repeat and take the average. That's it. Question 3. 2 substances, we have a solid E and a solution F, were analyzed. Solid E is iron 2 sulfate. Tests were done on solid E and solution F. So we already know what solid E is, so now we need to say what the expected observations are with these tests. So again, solid E is iron 2 sulfate. So we're looking for the Fe2 plus ion, and we're looking for the SO4 2 minus ion. Okay, the sulfate ion, the iron and the sulfate. A, describe the appearance of solid E. Okay, well, the iron sulfate solid is a pale green solid. It is pale green. You can just say it's green if you like. That also works. And you could say it's a pale green solid, or you could say they're pale green crystals, because iron 2 sulfate is a salt, and salts are in crystals. That works. Solid E was added to distilled water in a test tube. The test tube was shaken to dissolve solid E and form solution E. Solution E was divided into 4 equal portions in 4 test tubes. So there were 4 different tests done on solution E. B. Dilute nitric acid and aqueous silver nitrate were added to the first portion of solution E. And so what do we see? What are the observations? Remember, whenever it says observations are what you see, smell, hear, something like that. Okay, they're not what you know. So if you see bubbling, you don't say carbon dioxide was given off. That you know that that's what it is, but that's not an observation. You can say bubbling or fizzing or effervescence. I'm not saying that's what happens here, but that is an example of something that they're very picky on. If they want an observation, they want it to be something you see, smell, hear, not taste. You don't taste them, obviously. Okay. And so dilute nitric acid and aqueous silver nitrate, what do those test for? Well, those are the tests for the chloride, the bromide, and the iodide ion. Okay, for chloride it goes white, for bromide it goes cream, and for iodide it goes yellow. Well, there's none of those in iron 2 sulfate, so you would see no reaction. You could say no change, no precipitate, that would all work. Okay, C. Dilute nitric acid and aqueous barium nitrate were added to the second portion of solution E. What is that test for? Well, that test is for sulfate. So you have your barium nitrate plus FeSO4, and you will have one of the things that will be produced, you'll have barium sulfate. Okay, you'll have barium sulfate produced plus iron nitrate. Well, barium sulfate is an insoluble solid. So it's a solid. It's insoluble, it'll be white precipitate. Okay. D, an excess of sodium hydroxide was added to the third portion of solution E. Well, when sodium hydroxide is added to iron sulfate, you do get a precipitate. And as iron is green, you get a green precipitate. Okay, and E, an excess of aqueous ammonia was added to the fourth portion of solution E. Again, when ammonia is added to iron sulfate, you also get a green precipitate. Okay, now every single chemistry practical exam or alternative to the practical exam will have something about identifying ions. You just need to memorize or learn the ions that you need to identify. Sometimes you can do a good explanation. Sometimes it's easier just to remember what is produced and then figure it out a bit more at A level of why it happens. Okay, but that is that bit. But we had two solutions we needed to figure out what they were. So now we do the tests on solution F. And solution F was an aqueous salt solution. Some of the tests and observations are shown. All right. So solution F was divided into 2 equal portions and 2 test tubes. So we had tests on test tube 1 and on test tube 2. In test tube 1, we had drops of aqueous sodium hydroxide added to the first portion of solution F, and that formed a white precipitate. And then when an excess of sodium hydroxide was added to the mixture, the white precipitate stayed insoluble. All right. That looks like it could be, as it's a white precipitate, and with excess sodium hydroxide it was still insoluble. That sounds like it is calcium 2+. But we will check with test 2. So an excess of aqueous ammonia was added to the second portion of solution F. No precipitate was formed. That still sounds like calcium. So what conclusion can you draw about the cation present in solution F? And the way that I always remember with cation, we have CATION, putting brackets around the T. A T looks an awful lot like a plus. So this is a positive ion. So this sounds like it is a positive. So you could say solution F contains, we talk about the cation, so it's a calcium ion, or you can say Ca2+ ion. All right, there we go. And question 4. This is the planning and investigation question. Now with this question, it's important that when you're writing out your answer, you're organized about it. If you're planning an investigation, you probably need it in a certain order. So before you start writing anything on this piece of paper after you've read the question, on those lines, turn to one of the blank pages, because there's always a blank page, and start planning out what you're going to write. So that way, if you find something, you don't have to say, oh yeah, and this part goes up here, and then, oh yeah, I should put this part down there. The easier it is for the examiner to read, the more likely they're going to find the marks and give you the marks. But don't forget, once you've finished doing your planning on one of the blank pieces of paper, always put a big line through it so that the examiner knows that it's rough work and it's not meant to be marked. It was just you're scribbling down to figure out what you were going to write. So what is this experiment for question 4? So aqueous solutions of barium hydroxide are alkaline. Okay, so barium hydroxide, Ba is Ba2 plus, hydroxide is 1 minus, so it's BaOH2. Plan an investigation to find the concentration of an aqueous solution of barium hydroxide. You are provided with an aqueous solution of barium hydroxide and dilute hydrochloric acid of a known concentration. So hydrochloric acid, HCl, okay, and common laboratory apparatus. It doesn't say anywhere here to list the laboratory apparatus, which means you should not list the laboratory apparatus. It's not asking you to, it's just planning the experiment. It also doesn't say anywhere here to write out the equation. Sometimes it does, sometimes it doesn't. And this was when it doesn't, I'll write it out anyway, just so you can see it, but you don't need to do that. Okay, this is just for your benefit. So in this reaction, basically we have barium hydroxide, BaOH2, plus HCl. We have an alkali plus an acid, produces a salt. So that will be BaCl2, because barium is +2, chloride is -1, so they swap. Plus, so alkali plus an acid produces salt plus water. Balancing this out, we have 2 chlorides here, so we need 2 HCl's here. Okay, if we have 2 HCl's, that means with the H's, we have 2 H's here, 2 H's with HCl and 2 H's with the barium hydroxide. It means we need 4 H's. So that means we have to put a 2 in front of H2O. Well, that means that we have 2 oxygens, and we have 2 oxygens with the barium hydroxide. We have 1 barium on each side, so it's balanced. So this is the equation that you're working with. So what you're trying to do, you know what the concentration of this is. You don't know what the concentration of that is. And you know that this is pH 7 because it's just a neutralization reaction. So what you need to do is a chemist's favorite experiment. It comes up so often in chemistry. Chemists love this experiment. It's called the titration. Chemists love titrations. So you really should know how to plan a titration. It comes up so often. I don't know if it'll come up this year though, so but it often comes up. Okay, so a titration, you add a known amount of something in a burette into an unknown amount of something else into a conical flask. Oh, sorry, this should be full. It's not. I should have some solution in. You're adding it in slowly, and in here there's an indicator. And when the indicator changes color, you know that you've reached the end point, and you can calculate the concentration of the unknown using the volume of the one that you know that was used and the mole ratio of the equation. All right, so that's what's happening. Now let's plan it out. So starting off, you need to put some of one solution into a burette. So it can be either the acid or the alkali. It doesn't really matter. But you don't, when you're planning an experiment, we don't say put some acid into the burette. You have to choose a number. So just choose a number that sounds reasonable. I'm going to say 50 centimeters cubed. So put 50 centimeters cubed of hydrochloric acid into a burette. All right. I'm going to then measure out 25 centimeters cubed of barium hydroxide into a conical flask. Okay, because we don't know whether the barium hydroxide is stronger than the acid or weaker than the acid. We just don't know. So I'm putting more of the hydrochloric acid in, but if you need more, if you want to put the same volumes in, that's fine. You can always add more hydrochloric acid to the burette. That's fine. All right, so once we have, you'd also say it doesn't have to be into a conical flask. It could be into a beaker. As I said, you could put the barium hydroxide into the burette and the hydrochloric acid into the beaker. That works as well. It doesn't matter. Do you write out the full barium hydroxide, or do you write out BaOH2? Well, it depends really on how confident you are that the formula for barium hydroxide is BaOH2. If you are even the slightest bit uncertain, maybe you're sort of saying, well, maybe it's BaOH. If you wrote BaOH, you would lose a mark because that's wrong. If you wrote barium hydroxide, that's right. They do not ask for the symbol equation. Okay, so you only write out BaOH2 if you're 100% certain that that's the answer, if that's not what they're asking for. Because you don't want to lose a mark for something that they're not asking for. If it's wrong, you lose a mark. Okay, now into the barium hydroxide, you need to add an indicator. And you can use almost any indicator that you know of. Okay, I'm going to say use methyl orange. So add methyl orange indicator to the flask. It doesn't really matter which one you use as long as it's not universal indicator, because universal indicator has a wide range of colors it changes. And you want something with a nice sharp endpoint. Okay, you don't want to have a variety of different colors that it can go to. They will just not give you a mark if you use a universal indicator. Okay, so you add methyl orange to the flask or something else, and then you add the acid gradually, slowly, or dropwise to the alkali. So you add the acid slowly until the color changes from yellow to pink. So yellow to pink, the reason why is because yellow is the color for the barium hydroxide, the alkali, and pink is the color when it's acidic. So you want to be able to, you need to add it slowly so you can find the exact drop where it changes between being alkali and being acid. Okay, so you want to take a note of the final volume, the initial volume, and calculate the volume of the hydrochloric acid that was added. So note the final volume and initial volume of the HCl to find out the volume of HCl added. Okay, once you've figured out what the volume of HCl was added, you can calculate the concentration of the HCl. Or you all know, calculate the number of moles of HCl used. You already know the concentration of the HCl. It's given to you. So calculate the number of moles of HCl used using the formula moles equals concentration times volume. And you can figure out the number of moles of barium hydroxide using the mole ratio in the equation. You don't need to write what the mole ratio was because they didn't ask you to write out the equation. So calculate the moles of alkali reacted using the mole ratio in the equation. And then at the end, what you're trying to find is the concentration of the alkali, so you can calculate the concentration of the alkali again using moles equals concentration times volume. And remember, you know the volume of the alkali because you said you measured out 25 centimeters cubed of barium hydroxide at the beginning. You know the moles because you just calculated from the number of moles of hydrochloric acid and the mole ratio. And then you can figure out the concentration. All right. And that is the end of this exam. I hope you have found this useful. I hope it will help you with your exams. If you do like it, if you think it's useful, please press the thumbs up, and would really appreciate it if you'd subscribe if you haven't subscribed already. If you have any questions or comments or anything else you'd like to say to it, we love hearing from you. So please write them in the discussion section below, and have a great day.